an inverse function will be extremely relevant once we start studying exponential functions. We'll want to abstract away the idea of finding the inverse to construct a new type of function. We don't get to these notes today. So, in order to motivate the idea of finding an inverse function, let's do something that might feel a little bit redundant. Let's suppose that you wanted to solve the equation x cubed plus 2 is equal to 1. That's like an equation you know how to solve? Yeah. Should I go through the walk of solving it, or do people just want to go to town? People want me to do some algebra? Cool. So, those who don't want to listen and just want to do it. Let's try to solve this. So remember, like, solving for x, like, your goal is to get x on its own. So it seems like a good forced move if you want to get x on its own. Get that 2 over to the other side, leaving you with x cubed equals negative 1. What undoes cubing? Cube rooting. So it sure looks like x will be the cube root of negative 1. Oh, but what is the cube root of negative 1? Still negative 1, right? Because negative 1 cubed is negative 1. So this equation is solved by x equals negative 1. Go through and solve that next line. X cubed plus 2 equals 7. Once you see what x is, go ahead and share. So, what are people getting? I guess either exact value or decimal approximation if you want. Cube root negative 9. And just because I already see you busting out your calculator, what is that about? Negative 2.1. And that makes sense, right? Because 2 is the cube root of 8, so it should be negative and a little bit more negative than negative 2. Nice. So you may have noticed something while doing that. It seemed like there was an awful lot of replication of effort. You did the exact same steps to solve the second equation as you did the first time. How many people here are doing like a computer science-y degree? Or have interest in computer science? All right, well, this is a thing that's important to avoid in all fields. You want to avoid replication of effort where possible. You should do things efficiently. If there's something that you know you'll have to do lots and lots of times, just do it once in advance and abstract, and then do it for all of these special cases. That's exactly what we'll do right now. So, if let's say we had many equations like this to solve, then maybe it would be more efficient to just solve this equation. And then we could plug in different values of y and figure out what x had to be. If you did that, I think you already know what you'll wind up with. I guess you'll subtract the 2 over and then take a cube root. That seemed pretty reasonable? Here's the payoff. That means that if you ever need to solve an equation that looks like this, you don't have to solve it. You have a formula that gives you the solution. Just plug in the choice of y that you want and go to town. If you want to solve x cubed plus 2 equals 2, well, you know what the solution should be. here's your choice for y. So you'll get x equal to the cube root of 2 minus 2, also known as 0. That idea feel pretty reasonable? And this is exactly what the concept of an inverse function is. An inverse function is the idea you have some equation you want to solve many times, solve it in abstract once, give the name of the solution, give the solution a name, call it f inverse of x, and then you can just use this formula. So, the idea of the inverse function. Whenever you have an equation, f of x equals y, and you would like to solve it to get x as a function of y, you're finding an inverse function to f of x. This new function will be denoted f inverse of y. So notice now this thing that is y is now the input. It's what used to be the dependent variable is now the dependent variable. Let's see about finding the inverse function for some examples. Right, so since the independent variable is called y, I usually want x to be the independent variable, so often we'll switch the role of x and y when we find the inverse function. So let's do that. Let's find the inverse function to this. F of x equal to 3x minus 2. So here's the procedure I'll follow. First, I'll switch the role of x and y, just because you may as well do that first. So this equation will become x equal to 3y minus 2. That looks like an equation you can solve for y. In fact, should I go through the walk of solving it for y, or should I just be quiet for a moment and you'll tell me what the solution is? Should I go through the algebra? Cool. I'll talk through some algebra. So, you want to solve this to get y on its own. What seems like a good first step? So right now, all the y's are on this side, and there's complicated stuff. If you look at that side, you start with y, you multiply it by 3, then you subtract 2. So the first thing to do is to undo that subtraction by 2. How do you undo subtracting 2? Add 2. So add 2 to both sides. You wind up with x plus 2 equals 3 multiplied by y. How do you undo multiplication by 3? You divide by 3. X plus 2 over 3 equals y. Here is the inverse function. F inverse of x for this particular function is equal to x plus 2 over 3. So in general, if you want to find the inverse to a function, there are two steps, two things to do. Swap the role of x and y, and next, solve for y. Those ideas make sense? Do you think it matters what order you do those two steps in? As written, I suppose, but you could do things in the opposite order if instead you wanted to start by solve f of x equals y for x, and then swap x and y. Take your pick, whichever feels more natural. All right. People feel pretty good? Cool. So let's see some subtleties. All right, so this is like, the goal is solving an equation. Not every equation can always be solved, and sometimes the solution doesn't behave correctly. So inverse functions won't always exist, and let's see an example where something goes wrong. So let's try to find, so here this example is going to say find inverse to f of x equals x squared. So let's try to do that. There's x squared equals y. If you wanted to follow the algorithm to find the inverse function, what's the first step to do? Swap y and x. So this becomes y squared equals x, and you would like to solve for y. So what should you do? Square root undoes square. Well, kind of. So you'd wind up with y equals, I'm leaving a space, square root of x. What's missing? Plus or minus, right? Whenever you undo a square with a square root, you forget whether the thing is positive or negative. So y equals positive or negative the square root of x. Is that a function? No, a single input wants to give two different outputs. When you try to plug in x equals 1, y wants to take two values. This fails the vertical line test. This is not a function. So, that's kind of annoying, right? Sometimes you go and try to find an inverse function only to find out that you've taken the effort of solving the thing, but the thing that you got isn't a function. And sometimes life just isn't perfect like that. So what I want to introduce next is a property that will determine exactly when inverse functions exist. And it won't be a fancy idea. The whole motivation will be something to do with the vertical line test. So let's try to I'm going to write down a definition, and then we'll try to explore what it means graphically. So a function is called one-to-one if every two distinct x values result in distinct values for f of x. So that's a lot of words, and the logic in the statement is a little bit complicated. A function is called one-to-one if whenever you take two distinct x values, you always get two distinct y values. So a function is not one-to-one if there exists a single pair of distinct inputs that give the same output. So let's go back to thinking about x squared. Can you think of two distinct inputs for x squared that give the exact same output? What's 2 squared? 4. What's another number whose square is 4? Negative 2. There's an example. So here's one. X equals 2 and x equals negative 2 are two distinct inputs with 2 squared equals negative 2 squared. So is this function one-to-one? So a lot of times I'll be a little bit shorthand and lazy and write 1:1 meaning one-to-one. Sometimes I might also accidentally say injective meaning one-to-one. That's just a fancier, more Latin-sounding word that means the same thing that sometimes mathematicians use. I'll try to stick with one-to-one for the sake of consistency of language, but I'll probably slip up at some point during this class. Folks feel okay? Nice. So that's what it means for a function to be one-to-one. A function is one-to-one if whenever you take two different inputs, you give different outputs. So a function is not one-to-one if there exist even two different x values that give the same y value. So with that in mind, let's do some things graphically. So here are some graphs of functions. Are these functions one-to-one? So remember what one-to-one means. A function is one-to-one if every time you take two different x values, you get the exact same y value. So here's this one. Is this function one-to-one? No, why not? Yeah, I see 3 distinct points where the function is equal to 1. 3 distinct inputs give an output value, a y value, of 1.